My name is David MacAlpine. I'm the director of the UCL Ear Institute, and I'm also the professor of auditory neuroscience. I first got interested in hearing and hearing research when I was a student, and I worked in a laboratory on my summer holidays that was investigating how certain medicines actually make you deaf. So for some medicines that are working against cancer, for example, they have a side effect that actually damages your inner ear and makes you deaf. And ways of understanding how those medicines work and how you can stop them making you deaf while they're making you better, or at least treating your cancer, is actually an important aspect of some of the work we do here. So the things that make you deaf are actually interesting in understanding how the inner ear works, and also interesting in understanding how we can stop those things making you deaf. They are medicines for other conditions, so we don't want the side effect to be deafness. We want to be able to keep people healthy and keep them hearing at the same time. So we obviously need our ears to hear, but actually we hear with our brain, not just our ears. Our ears are picking up the sound and transmitting them the information about sound to our brain in the form of electrical pulses, but our brain is creating the sense of sound. It's creating where things are in space. It's telling us about what people are saying. It's helping us understand the environment in which we're listening. And our brain is one of our major organs for hearing, not just our ears. So your outer ear is very important. It's not just for keeping your glasses on. The outer ear has very important functions. One is to help you hear sounds that are quiet, so it acts like a radar dish, if you like, and picks up quiet sounds. And the other is to help you tell where sound sources are located, above you or beneath you. So sound energy hits the outer ear and is transformed, and when it gets to your eardrum, it's got particular sound energy increases or reductions depending on where the sound source is located. So a sound that's above you generates a different pattern of energy interactions at the outer ear than does the same sound source beneath you. So your outer ear helps you tell whether a sound is above you or beneath you, and that's a very important cue for localizing sounds. The middle ear is an air-filled space with several bones in it that transmits sound from the outside world to your inner ear. And the inner ear is a snail shell coiled structure inside that essentially contains all of the sensory cells and neurons, the nerve fibers that actually transmit sound to your brain. Sound energy is collected by the outer ear and transmitted down the ear canal to the eardrum. And inside the middle ear there are three bones, the malleus, the incus and the stapes, and they connect from the eardrum to the oval window of the inner ear. So the sound vibrations that move the eardrum are transmitted as vibrations of those three bones into the oval window of the inner ear, and the vibrations are eventually turned into electrical pulses that are fed down the nerve to the brain. Many people who are deaf have problems in the inner ear. The sensory cells that are turning vibrations into electrical pulses and feeding them to your brain are actually damaged. And when those are damaged, it's very hard to repair them. So in fact, it's not yet possible to repair them. We have to look after them and try not to damage them. So loud sounds, certain drugs, and getting older tend to damage those sensory cells, and that's why our hearing can be impaired. And especially loud sounds in this modern age where we listen to iPods and lots of loud music can really damage our hearing well before we would assume that our hearing would be lost. Other than preventing hearing loss, the therapies that we have for hearing loss at the moment are hearing aids and cochlear implants. Everyone knows about hearing aids. This is a way of boosting the sound that's actually getting to your ear because your inner ear is damaged. If you have very severe damage to your inner ear, that won't help, and you'll need something called a cochlear implant. That's called electrical hearing. And these are devices which essentially are feeding electrical pulses into your inner ear and stimulating the neurons directly. That's because your sensory cells have all died or they're all damaged. So electrical hearing is one way of getting over that problem of severe or profound hearing loss. But it doesn't produce the same sensation of hearing as we have normally. And it's very hard to appreciate music and speech in noisy environments. So listening to other people speaking when there's lots of noise, listening to music, not very possible with hearing aids or cochlear implants. Currently, there are not very many biological therapies for hearing. In fact, we don't really have any. And what we need to do is develop those pills and those therapies that actually prevent hearing loss in the first place, or protect our hearing, especially if we have to work or in noisy environments, or we're listening to noisy sounds all of the time. But finding a way of giving a pill or some other therapy that reverses hearing loss is actually a major part of our research here at the Institute. And many people around the world are looking for those sorts of therapies and pills that will essentially prevent hearing loss or restart hearing if you've actually lost it. As a scientist, I would like to invent something that turned down the volume of the sound automatically so that it didn't damage our hearing. Often we don't know when a sound is damaging our hearing, and if we had some device that actually could detect that and turn down the volume of the sound even at our ears, then we would protect ourselves from hearing loss in the first place.